guys, today we're going to do section 2.8, which is related rates, and as I mentioned in the last section, that is word problems, and so I know they are super pumped about that. We are going to go over some steps and some strategies to kind of help us work through these word problems, and what you learned in section 2.6 for implicit differentiation is going to be part of this. So we'll kind of talk about how that is different for this section compared to section 2.6 as we go through these strategies. So if you look here, your problem solving strategies, the first one is read the problem carefully. As you read, you may even want to underline things that stick out to you, information that you know that you're going to need to use. Draw a diagram if possible. Sometimes, honestly, a diagram isn't that necessary if you have the formula, but I would always draw one if possible, and some of the problems they're going to give a diagram for you, so that's helpful. Notation, assign symbols to all quantities that are functions of time. So keep in mind, as we do implicit differentiation, we are taking a derivative, which is rates of change. And so when we did implicit differentiation in section 2.6, we were always taking the derivative with respect to with respect to x. So anything with a y, we tacked on a y prime or a dy over dx. In this section, everything that we do will be a derivative with respect to time, and we're going to talk about that again in a second. So express the given information and the required rate in terms of derivatives. So whatever formula you decide that you need to use, then you'll take the derivative of that. That's going to come in number 5. Write an equation that relates the various quantities of the problem. If necessary, use the geometry of the situation to eliminate one of the variables. So if you have too many variables, and you'll know what I mean as we work through some of these, then you'll want to rewrite so that you have one less variable. And then it says to use the chain rule, which really we are using implicit, okay, to differentiate both sides of the equation. And again, with respect to t is very important, because every variable that you take the derivative of, you are going to tack on what was d prime. So in other words, if we're taking the derivative of an x, you're going to tack on dx over dt. If we're taking the derivative of y, you're going to tack on dy over dt. If we're taking the derivative of v for volume, you're going to tack on dv over dt. So keep that in mind. Substitute the given information into the resulting equation and solve for the unknown rate. Alright, so, and again, we'll go through these steps as we do each of these, so no need to really memorize those steps, okay? We're going to work some examples that are straight from your book. Some of these are a little more complicated, and then we're also going to work some out of the homework in your book, and some of these will be closely aligned to the problems in your WebAssign, so that will be helpful to you as well. So this is kind of a lengthy section, and especially since they're word problems, they take a little longer anyway, so I may even split this video up into 2. I'm just going to kind of see how time goes as I record this, okay? Alright, so example 1 says air is being pumped into a spherical balloon. So obviously the fact that we have a sphere is important, so that its volume increases at a rate of 100 centimeters cubed per second. Okay, how fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay, so we're dealing with the volume, and specifically we are dealing with the volume of a sphere. Okay, so you know that that is the formula that you're going to need to use. Now that doesn't they don't give that to you in this problem, but I will make sure that you have the formulas that you need for your test. And on your homework, if that formula is not given to you, it should be a formula that we've already used in our notes and in the examples that we've worked together. So, and then same thing for your test as well. I'm not going to give you anything crazy with a formula that you haven't already used, okay? Alright, so we're going to say that this is given, and the formula for volume of a sphere is V equals 4/3 pi r cubed, okay? So So we're just going to hold tight to that. That is the formula that we're going to use. So you're going to label what you know, okay? So if they tell you, hey, this is the diameter, this is the radius, then you know that that's your D and your R, okay? But if they tell you this is the volume increases at a rate, the radius increases at a rate, then you're looking for the derivatives, okay? You're looking for dV over dt, or they've given that to you, okay? So here, if the volume increases at a rate of 100 centimeters cubed per second, then they have given us dV over dt because the volume increases. That is a rate of change, and it is the rate of change of the volume, okay? So we're going to label what we know. So dV over dt is 100 centimeters cubed per second, okay? How fast is How fast is the radius of the balloon increasing? So again, we want to know how fast is the radius increasing. So we're wanting to know what is dr over dt. We're looking for dr over dt, okay? When the diameter is 50 centimeters. So if they told us that our diameter is 50, that's all the way across the balloon, right? Or all the way across the circle. So radius is what? Half of that. And I want to make sure I write my radius down because my original formula has radius in it. So I'm not going to be using diameter. I'm going to be using radius. But because they give me the diameter, then I know the radius is half of that, which is 25 centimeters, okay? So once you figure out, okay, hey, this is the formula that I need to use based on the shape that I have. Here's all of my information that's given in the problem that I've labeled. Then you are going to take the derivative of the given equation. Take the derivative of the given equation, again, using implicit, okay? And then once you take the derivative, you're going to plug in the information that you know and solve for the unknown, okay? So the derivative of v would just be 1. But remember, we have to, everything is in respect to time. So the derivative of v is 1. So this will be dv over dt. All right? Then remember that pi is just a number. Okay, so all of this is just a number, and here's your variable r. So I would bring that 3 out in front and multiply that 3 times 4/3 and leave my pi. And then once I bring that out in front, I subtract 1. So now I have r squared. Now I have r squared. And again, when I take the derivative of r with respect to time, then I have dr over dt. Okay, so now simplify and pretty things up. So these 3's cancel, right? And I'm left with 4 pi r squared dr over dt. Okay, so this is my derivative of my original function. Okay, now plug in what information you know from over here where we labeled. Okay, so dv over dt is 100. All right, 4 pi r squared. That's going to be 25 squared. And bring down your dr over dt. Now, we're going to leave pi all the way until the very end because sometimes in my, I was about to say my math lab, sometimes in WebAssign, they want you to leave it as pi, and sometimes they want it as a decimal. So I'm going to show you how to do both so that regardless of how they ask for the answer, you know how to do that, okay? So we're going to say 4 times 25 squared. 4 times 25 squared, and that's going to give us 2500 pi dr over dt. Then we're going to divide, because we're solving for dr over dt, we're going to divide by 2500 pi. So then 100 over 2500 reduces to 1 over 25 pi. Okay, and that is centimeters per second. Oh, sorry, off the screen. That reduces to 1 over 25 pi, and that is centimeters per second. Okay, or if you put this in your calculator and get a decimal, then that is approximately 0.0127 centimeters per second. Okay, so regardless of in WebAssign, if they want you to leave that with pi in your answer, or if they want that as a decimal, okay, then you can enter that. Now, you're going to be tempted to put in your answer like this, okay, 1 over 25 pi, okay, but remember, order of operations matters, so how we put it in our calculator matters. So you do not want to enter it this way. You see that you do not get the right answer that way. You want to say 1 divided by, in parentheses, 25 pi, okay? Because that way you're saying 1 divided by all of that instead of 1 divided by 25 and then multiplying that answer times pi. And then you see that that gives you the answer that we have here, okay? So just be mindful of that. Make sure that you put your stuff, your junk in the denominator in parentheses, okay? Make sure that you're putting that in parentheses. All right, so that is example 1. That is example 1. All right, so let's flip it over and move to example 2. Let's look at example 2. All right, again, same process, okay, but we're dealing with a different shape, so that's going to change things a little bit. So we have a ladder that is 10 feet long, okay, and that's resting against a vertical wall. So we know that if we have a ladder resting against a vertical wall, that is going to form what kind of shape? That is going to form a right triangle, okay? Those of you who took trig, that is not a shocker, okay? And even in college algebra, y'all did problems like this as well, okay? So we have a ladder resting against a vertical wall, okay? So that gives you your shape. We'll label it in just a second. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Now that sounds like blah, 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 right? But as we work through this and as we label things, you'll see that it's really not so bad. So a ladder is 10 feet long. So I always call this my X and this my Y, because if that were on a coordinate plane, then that is what it would be. So I always call this my X, this my Y, and this my Z. Now if you do watch it or look at some of your examples in WebAssign, they may label those a little differently. It's not wrong as long as everything matches up based on how you label it. But just for consistency, I always label my horizontal as X, my vertical as Y, and my hypotenuse as G, as Z, not G. Z, just for consistency, but again, that's not a deal breaker. So I know that Z is 10 feet, okay? If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, so where the ladder is sliding away from the wall is at the bottom, and that is a rate, okay? So that's a derivative. So that means that your dx over dt is 1 foot per second. Your dx over dt is 1 foot per second. Okay? How fast is the top of the ladder sliding down the wall? So what they want to know is what is that rate that it's sliding down the wall? What is dy over dt? Okay? When the bottom of the ladder is 6 feet from the wall, so when x equals 6, then what is dy over dt? Okay? So we know that if we're dealing with a right triangle, that we're going to be using Pythagorean theorem, right? Most likely, unless we're using a trig function, and we'll work one like that later. So that means that this is going to be x squared plus y squared equals z squared. Now we're going to talk about taking the derivative of that and plugging in that information in just a second. But if you know that you've got x, y, and z, we obviously need all three of these pieces, right? So we're missing y and we need y. So we're going to use Pythagorean theorem to find y, but then we're also going to use Pythagorean theorem as our formula that we're going to take the derivative of using implicit. Okay, so let's find y. And that's going to be 6 squared plus y squared equals 10 squared. So that's going to be 36 plus y squared equals 100. So 100 minus 36 is going to be 64. And take the square root. So we're getting y equals 8. We're getting y equals 8. Again, remember this is your wall. Okay? And so y equals 8. All right, so we have everything that we need. Now we're ready to take the derivative of this, okay? But when you are setting up your formula, anything that is a constant that does not change, you're going to plug into your formula from the beginning, okay? So for instance, this ladder is sliding down the wall. So this y value is changing. This x value is changing as the ladder slides down the wall. What is not changing is the length of the ladder, okay? So even though that ladder is sliding down the wall, it's not shrinking, okay? It's not getting any shorter. It's not getting longer, okay? It's staying at 10 feet. So that means that we really have x squared plus y squared equals 10 squared. So that gives me x squared plus y squared equals 100. So now this is the formula that we're going to use. That's the formula we're going to take the derivative of, okay? And out to the side, I'm going to put here ladder length is not changing. That way, when you go back and look at these notes, you'll remember why we did that. You'll remember why we did that, because in a few minutes, we're going to work another example that is a right triangle, and all three values are changing. So you take the derivative of the whole thing as is, okay? But if you have a constant that is not changing, you're going to plug that in from the beginning, okay? So we did that. So this is your formula that you're taking the derivative of, again, with respect to time, okay? So the derivative of x squared is 2x dx over dt. The derivative of y squared is 2y dy over dt. Again, everything is with respect to time. And the derivative of 100 is a constant, so the derivative of that is 0. Okay, so this is my derivative. So now I'm going to plug in everything that I know and solve for what I do not, which in this case is going to be dy over dt. Okay, so 2 times x, and my x is 6. Dx over dt is 1. Plus 2 times y, we found your y to be 8. Dy over dt, that is what we are looking for, and equals 0. Okay? Alright, so 2 times 6 times 1. 2 times 6 is 12 times 1, that's still 12. 2 times 8 is 16. Dy over dt, again, that equals 0. Alright, so let's move our 12 to the other side, and when we do, I'm going to move this up a little bit, and when we do, that is going to make that negative. So we have 16 dy over dt equals negative 12, and then we're going to divide both sides by 16, and so then we get dy over dt. This reduces, 4 will go into both of those, to negative 3 over 4. And that is feet per second. Feet per second. Okay, so how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? It is sliding at a rate of negative 3/4 feet per second. Now, why did this end up being negative? Because we are going down the wall. Because we're going down the wall. Okay? Alright, so again, main thing on this is just remembering that when you plug in, if you have a constant, that ladder length isn't changing, that you plug that in from the beginning before you take the derivative. Before you take the derivative. Then everything else from this point down is exactly the same as what we did in example 1. Exactly the same as what, example 1. Okay. Alright, let's look at example 3. Let's look at example 3. Now, when we were going over these examples, when I was going over the strategies at the beginning of this section, I mentioned that sometimes you might have too many variables and you might have to rewrite so that you have less variables, okay? So that is what we're going to do here. Honestly, example 3 is probably the hardest example of this section, just for the simple fact that you're having to rewrite some things that on your own you may not recognize that you need to do. But now that we have worked one like that, then you should be able to recognize that, okay? You possibly have one like this on your homework. Pretty confident, I'll have to double check, but I'm pretty sure that you do not have one like this on your test, okay? But when you get that study guide, you'll have a better idea of what types of word problems to expect on your test, okay? Alright, so a water tank has the shape of an inverted circular cone, okay? So they have already given a diagram to you, so that is helpful. Okay, with base radius 2 meters and height of 4 meters. If water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. Now, they did not give you the formula, but I'm going to give that to you, and again, you would be given that formula on your test. So, volume of a circular cone is going to be V equals 1/3 pi r squared h. V equals 1/3 pi r squared h. Okay, now the deal with that is again we've got multiple variables here, right? So on this right side, when we get ready to take the derivative, we've got two things, and if we keep it the way it is, we would have to do the product rule along with implicit, so that could get pretty yucky, right? So if there's a way that we could rewrite that so that we have one less variable, then that is going to be our goal, and that is what we are going to want to do, okay? So let's look here. If you notice here, you've got a proportion. You've got R is to H as 2 is to 4, okay? So R over H equals 2 over 4, okay? So what we can do is we can solve for R and rewrite this, write R in terms of H. And so then we can plug in one thing in for the other into our main formula so that we only have one variable. So if we multiply both sides by H, then they cancel here, and we get R equals, and what happens? 2 over 4 reduces to just 1/2, right? So then that would just be H over 2. So we have rewritten R in terms of H. So now I can take this and plug it in, and I will only have one variable over here. All right, and so that will be very helpful to us, okay? So I'm going to write in parentheses, plug in, so you'll remember that that's what we're going to do with that. And the reason why we're doing that is because we need less variables. We need less variables. That's why we're doing this. Okay? Alright, so again, before we take the derivative, we're going to take this and plug it in, alright, so that we can get a simpler equation to take the derivative of. Okay, so we have V equals 1/3 pi. And we're plugging in h over 2 for r. So that means h over 2 squared times h. All I did was take h over 2 and plug it in for r. Okay? So now this gives me v equals, bear with me, I'm going to do a couple of things in one step. So 2 squared, because this whole thing is squared, right? So 2 squared is 4, and 4 times 3 is 12. So this gives me 1 over 12 pi. And if this is h squared and this is h, then that gives me h cubed. That gives me h cubed. Okay? So now I have rewritten this so that I only have one variable on the right side, so that's going to make my life a lot easier. Now I'm ready to take the derivative and plug in. I'm ready to take the derivative and plug in, same as we've been doing in the other questions. Okay, now before I do that, I did not label everything from our problem down here. Okay, so let's do that real quick. Alright, a water tank has the shape, blah, 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 with a base radius of 2 and a height of 4. We already have that here. Okay, if water is being pumped into the tank at a rate of, so that is your dV over dt, and that's 2 meters cubed per minute. Find the rate at which the water level, so your water level is your height, so we're looking for dH over dt. We're looking for our dH over dt when the water is 3 meters deep. So when your h is 3 meters. Okay? So now we've labeled everything, so now we can take the derivative, and once we take the derivative, we'll plug all of this stuff in. Okay, so the derivative of v is 1, but that's going to be what? dv over dt. The derivative of the right, I'm bringing this 3 out in front, so 3 times 1/12 is going to be 1/4, so that's going to be 1/4 pi h, and we're going to subtract 1, so that's going to give me h squared. And then when I take the derivative of my h, I'm going to add on dh over dt. Okay? Alright, so now plug in what you know. dv over dt is 2. I'm just going to make this prettier and make that pi over 4. My h is 3, so I have 3 squared dh over dt. So that gives me 2 equals 3 squared is 9, so that gives me 9 pi 4 dh over dt. I need to get rid of this 4 on the bottom, so I'm going to multiply it times that 2. That gives me 8 equals 9 pi dh over dt. Divide both sides by 9 pi, right? And so that gives me 8 over 9 pi equals dh over dt. Or if you're putting that in as a decimal, then 8 divided by 9 pi is going to be approximately 0.28. Okay, 0.28. Again, when you put this in your calculator, you're going to want to make sure that you do 8 divided by 9 pi in parentheses, right? 9 pi in parentheses. Alright, questions on that? Alright, I'm going to go ahead and stop here and let you kind of digest that a little bit, and then I'm going to make a second video that is going to be the last 2 examples from this section, 4 and 5, and then the examples from the book. And in fact, the examples from the book are shorter than the ones that we've done already, so those will go pretty quickly. Okay, so I try to keep these videos to about 30-35 minutes, so I'm going to go ahead and stop here, and then you can catch the rest of this section in the next video.